The Ampere Maxwell Law states that a magnetic field can be created by an electric current or a change in electric flux. We interpret the integral in this equation as follows. Sum the product of the components of the magnetic field parallel to a path around a boundary with infinitesimal portions of that boundary. The circle symbol denotes that this path is closed, meaning that the start and stop points of the integration are the same. The subscript line denotes that the integral is one-dimensional. Let's begin by using the Ampere Maxwell Law to determine the magnetic field from a current. If the change in electric flux is zero, then the magnetic field results from the enclosed current alone. Specifically, what this equation says is that the magnetic field around the boundary of a surface is determined by the net electric current passing through that surface. This expression is commonly referred to as Ampere's law. Let's consider the system shown in the figure in which there is a single current at the center of a circularly symmetric surface. The boundary for the surface will be a distance r away from the current, and the path for the boundary will be directed counterclockwise. This is the equation for Ampere's law for this system. The variable b in this equation denotes the magnetic field of the current at the boundary of the surface. The variable ds is an infinitesimal bit of length of the boundary, and the subscript line denotes that we are performing a one-dimensional integral around the boundary. In other words, the units of ds will have units of length. Finally, the variable I enclosed denotes the net current passing through the boundary. We can argue from symmetry that the magnetic field must be constant at all points along the boundary of the surface. In that case, we can remove it from the integral. We can further assume that the direction of the vectors b and ds in this equation are the same. We can then replace the dot product with simple multiplication and remove the vector signs. The closed integral of ds around the boundary is simply the summation of little bits of length around the entire boundary. This must be the circumference of the boundary. The substitution of all of these results into Ampere's law gives us the following final equation. We see from this equation that the magnitude of the magnetic field decreases as the distance from the current increases. We can then determine the direction of the magnetic field using a right-hand rule. Curl the fingers of your right hand in the direction of the path of the boundary, and the thumb of your right hand points in the direction of the associated area vector. Currents in the same direction as the area vector are positive. Currents in the opposite direction of the area vector are negative. Positive currents have counterclockwise magnetic fields, and negative currents have clockwise magnetic fields. Next, let's calculate the magnetic field from a change in electric flux. We will consider a parallel plate capacitor with circular plates as our model system for these calculations. We want to determine the magnitude of the magnetic field that is induced when the electric charge on the plates of the capacitor changes. Specifically, what is the magnitude of the magnetic field a distance r away from the center axis of the capacitor? Since there is no electric current between the plates of the capacitor, we can rewrite the Ampere Maxwell law in terms of the changing electric flux only. In other words, the magnetic field is induced when there are changes to the electric field between the plates of the capacitor. This is Maxwell's modification of Ampere's law. Next, let's define a surface for calculating the flux. This surface will be defined by the boundary path shown in the figure. The electric flux through this surface can then be calculated using the following equation. We see that for this path, the direction of the area vector is out of the page. Therefore, since the direction of the area vector and the direction of the electric field are the same, the equation for the electric flux through the bounded surface can be simplified to this expression. We will now assume that the capacitor is perfect, such that the electric field in between the plates of the capacitor is constant and 0 everywhere else. Therefore, if the radius of the boundary is larger than the radius of the capacitor plate, the electric flux is equal to E times pi times capital R squared. And if the radius of the boundary is smaller than the radius of the capacitor plate, the electric flux is equal to E times pi times little r squared. The substitution of these results into the Ampere Maxwell law gives us the following equations, which we can further simplify since only the electric field depends upon time. Now let's calculate the other term in the Ampere Maxwell law. As before, we will make a symmetry argument that the magnitude of the magnetic field is constant at all points along the boundary of the surface. We will further assume that the direction of the vectors b and ds in this equation are the same. We can then replace the dot product with simple multiplication and remove the vector signs. The integral of ds around the boundary is simply the circumference of the boundary. Substitution of this result into our previously derived equations gives us the following expressions, which we can then further simplify to these results. We see that when we are outside of the capacitor, the magnitude of the magnetic field decreases inversely with distance from the center of the capacitor. However, when we are within the capacitor, the magnitude of the magnetic field increases linearly with distance from the center of the capacitor. We can progress further by substituting the equation for the electric field of a capacitor. The variable A in this equation is the surface area of a plate of the capacitor, which is simply pi times capital R squared. We now see that the magnitude of the magnetic field depends upon the derivative of the capacitor's charge with respect to time. If the capacitor is charging, the direction of the magnetic field is the same as the direction of the path of integration. If the capacitor is discharging, the direction of the magnetic field is opposite the direction of the path of integration. Remember that the path of integration was defined so that the area vector pointed in the same direction as the electric field. This figure shows the magnetic field from the currents and the change in electric fluxes when a capacitor is charging and when it is discharging. As expected, the direction of the magnetic field switches orientation for these two situations. However, the direction of the magnetic field from the current is always the same as the direction of the magnetic field from the changing electric flux. Furthermore, the magnitude of the magnetic field from the current is the same as the magnitude of the magnetic field from the changing electric flux. We will see later when we discuss electric circuits that this is also a result of energy conservation.